students, in last class we have discussed about image formation in cases of refraction at plane surface, and at the end we talked about the shift that a glass slab produces. So, we have seen in which direction the shift happens and the magnitude that it has and concepts like that. So, now we will start off with a question based on that, and then we will move on to some more concepts related to refraction. Okay. So, let us see this question. They have given, they are asking us to find the final distance at which image is formed as seen by the observer. So, the object is here. So, this is the object, a point object, and at a distance of 10 centimeters there is a glass slab having a width of 15 centimeters, and from there at a distance of 20 centimeters we have a concave mirror having a focal length of 30 centimeters. So, we know that as the light ray passes and reaches the mirror, it undergoes multiple refractions, and what I am going to do now, because we have already understood what a glass slab does to the light ray. So, I am not going to consider one refraction here, one refraction here, again reflection here. So, I will directly assume that this glass slab, we know that if I draw a light ray, one which is anyways in the horizontal, the normal direction, and if I consider one more light ray like this, it bends towards the normal, again away from the normal, and eventually it appears to come from a point which is somewhere over here, right. So, that is what the glass slab does, it just shifts the position of the object according to the mirror in this particular scenario. So, I will directly find that. So, instead of considering refraction here, once again refraction here, I will directly consider that the light rays which are reaching the mirror are appearing to come from a point which is over here, and we know how to calculate the shift, right. So, let us do that. So, I will first calculate the shift produced by glass slab. So, the formula for that is T into 1 minus 1 by mu relative, right. So, in this case the thickness is 15 centimeters. So, 15 centimeters into 1 minus 1 by, so mu of slab with respect to surrounding. Surrounding is anyways air, which has a refractive index of 1. So, relative refractive index is just 3 by 2. So, divided by 3 by 2. So, when I substitute that, this becomes 2 by 3, and solving this will give me 15 centimeters into 1 by 3, which is 10 centimeters, sorry 15 centimeters into 1 by 3 is going to give me 5 centimeters. So, that is the shift that is produced by the glass slab. So, which means 5 centimeters from here, which will be somewhere over here. So, I should have drawn the ray slightly differently. So, this is how the final light ray travels coming out of the glass slab, and it appears to come from a point which is over here. It shifts by 5 centimeters. Okay. So, that is the scenario which we would be getting in this case. Now, I can say that this position will now act as the object for the mirror. So, that we know, because the light rays which are reaching the mirror, so this light ray and this light ray, so both of them appear to come from here. So, this is the object for the mirror. So, now let us write the mirror formula and find the image formed by the mirror. So, if I do that, 1 by u plus 1 by v is equal to 1 by f. So, let us substitute the values. So, what is u? So, in front of the mirror the object is at a distance of, if this is 10 and if it is shifted by 5, this is 5 plus 15 plus 20. So, 5 plus 15 is 20, 20 plus 20 is 40. So, I will substitute the value of u as minus 40 plus 1 by v is equal to 1 by, the value of f is given as 30, but because it is a concave mirror I will substitute it as minus 30, right. So, that is the expression which I get. So, solving this will give me v is equal to 1 by 40 minus 1 by 30, which is 40 into 30 with a negative sign, divided by 40 minus 30, which is 10. So, solving this is going to give me minus 120 centimeters, right. So, that is where the image is formed. Minus indicates that the image is formed in front of the mirror itself. So, which means these light rays after reflecting from here will reflect back I mean after coming back they will converge at a point which is at a distance of 120 centimeters. So, that is so far away. So, I will just draw it in the backward direction like this. So, this is how the reflected light ray would be. Now, one important thing which we will have to notice here is that the answer? Is this the final location where the image is formed? Is that the answer that we are looking for? They are asking us to find the final distance at which the image is formed. Are we looking for this image or something else? So, that is not the image we are looking for, because this light ray which is travelling through this slab will once again undergo refraction. So, this will once again undergo refraction and the glass slab will once again produce a shift. We discussed that glass slab will always shift the location of the object, right, by a distance of t into 1 minus 1 by mu. So, what happens is that whether the light ray is going from this side to this side, I mean from left to right or from right to left, the slab will always produce this much of a shift. And because we got the value as positive here, I have told you in last class, this positive sign indicates that shift will be in the direction of incident ray, right. So, initially when the light was going in this direction, from this position it was shifted by 5 centimeters, but this time the light rays are coming backwards. They are coming backwards to converge at a point which is 120 centimeters in front of the mirror. Now, what is going to happen? As it is passing through the glass slab will once again shift those light rays. Is that correct? So, the glass slab will once again shift those light rays in the same direction by 5 centimeters further. So, what we can say is that, so this is 120 centimeters in front of mirror. So, this is not the final result, that is what I was telling you. So, what happens is that these light rays are further shifted to produce the final image at a distance of 120 centimeters plus 5 centimeters, which is equal to 125 centimeters in front of mirror. Right. So, that is what happens in this particular case. So, when the light rays are travelling like this, slab shifts by 5 centimeters in that direction. When the light rays are coming back to converge at 120, so the slab will once again shift them in the direction of light rays by 5 centimeters, making them converge at 125 centimeters in front of mirror. So, this is the final answer that we should be getting. The final image is formed at a distance of 125 centimeters in front of mirror, right. So, students, we have discussed about the effect produced by one slab, the shift that it produces. So, now let us understand what happens if multiple slabs are placed adjacent to one another. So, we call such a system as a composite slab system, composite slabs, let us call it as. Okay. So, what I am saying here is the slabs are basically like this, touching each other one beside the other. So, if you have slabs placed like this, you can take n number of slabs also, but I will stick to 3 for explanation now. So, let us consider this as a system. So, the thickness of this slab is, let us say T1, the thickness of this is T2, the thickness of this is T3, and the refractive index of this is mu1, mu2, mu3. You can consider that the surrounding medium is having a refractive index of mu naught, and let us say there is an observer who is watching it from here, an object which is on this side. Now, we know that when there is a single slab, the position of this object as per the person will be shifted in the direction of light ray by a distance of t into 1 minus 1 by mu relative, or relative refractive index. Okay. So, in this particular case, when there are multiple slabs in this case, what we can do is we can consider this system as something like this. We can consider this as one slab separated by a very small distance and another slab which is placed adjacent to it, and again separated by a very small distance and again another slab placed adjacent to it. And I can assume that, so here the medium is having a refractive index of mu naught, and even the region between these two, that small thickness which I have considered, I can consider that is also filled with a medium of refractive index mu naught. And similarly here, this small thickness which I have considered, I will once again assume that it is filled with mu naught, and this side we anyways have a refractive index of mu naught. See, the reason why I am doing this is this formula which we have derived earlier, which is T into 1 minus 1 by mu relative, which is mu of medium or mu of slab divided by mu of medium, which means mu medium will go into the top. So, this is the expression which I have derived in last class. Now, I have told you few important points regarding this expression. This should be used only when the medium is same on both the sides of the slab. Medium is same on both sides. So, that is the reason I am viewing this particular system of composite slab system as a slab separated by a very small thickness, because even if there is a very small thickness of mu naught here, that is not going to affect the path of the light ray, because the thickness is very negligible. And similarly, second medium is negligible thickness of mu naught, again third medium, and then we anyways have the actual medium of mu naught. So, that is what I am going to consider. And now, if I consider a light ray which is passing through these slabs, it first experiences a shift because of this slab, then it passes into the second slab, experiences a shift due to that, then into third slab, shift due to that. So, in this particular case, we can say that the final light ray which travels from here, let us say it bends like this, and once again bends like this, and let us say once again bends like this, and eventually comes out in this manner. So, the final light ray, if I trace it backwards and find the point where it intersects the horizontal or the normal line, we will observe that the net shift that it experiences will be the sum of shift produced by the first slab plus shift produced by the second slab plus shift produced by the third slab. So, in this case I can write shift net is equal to, let me write it as S1 plus S2 plus S3. So, shift due to first, shift due to second and third respectively. Now, we can just write down the expression for that. We know that the shift produced by the first slab, because I am considering that it is surrounded by mu naught on both the sides, I have considered a negligible thickness of mu naught, which is not going to make any difference. So, by considering a negligible thickness of mu naught, so that is not going to create any kind of difference to the light ray passing through it. So, we can safely assume that. Okay. So, S1, what is the value I can write for S1? The shift produced by the first slab will be T1 into 1 minus 1 by refractive index of this with respect to the surrounding medium, which is mu 1 by mu naught. So, I can write it as mu 1 by mu naught goes to the numerator, and this is what we get, plus S2. What is the value of S2? Similar to this, I can write T2 into 1 minus mu naught by mu 2 plus third slab will produce a shift of T3 into 1 minus mu naught by mu 3. So, simply put, it is nothing but the sum of individual shifts produced by each slab altogether. Clear? So, that is what we understand as the net shift in this particular scenario. And remember, once again, to be able to apply that final result which we have used there, the medium which we have here and the medium which we have here should be same. Clear? Only then we will be able to understand that in this particular scenario. So, the initial medium and the final medium. So, let us call it as initial medium, the one where the incident rays are originating, and this one will be the final medium. So, this is applicable only when the initial medium and final medium have same refractive index. Only then we can consider that whatever is the mu naught here, we can consider a negligible thickness of mu naught and understand these as 3 individual slabs and find the shift produced by each one and then add them. Clear? So, what if the medium initially and finally are different? What do we do in such a scenario? So, I will just write it down here. If the initial and final media are different, or let me write it as media have different refractive indices, then final image should be calculated by considering successive refractions. So, that is the only method we have in such a scenario. So, if the initial medium and final medium are different, then there is no way we can use this particular method. Clear? So, we will have to first find the image formed due to refraction at this surface, take that as the object for this surface, find the image, that will be the object for this, find image, that will be the object for this, and so on. So, that is the idea. So, please keep in mind that this is applicable only if initial and final media have same mu. So, that is the idea. So, just calculate the net shift by adding individual shifts, right. So, students, now we will talk about one more effect that a glass slab produces when light is incident on it. So, it is called as lateral shift, right. So, what it basically means is, so if I consider a glass slab like this, let us say its thickness is some t, we can consider that the refractive index is some mu, right. And in this particular scenario, if light ray is incident on this glass slab, let us say this is the normal and light is incident like this. So, this is the incident ray. So, having an angle of incidence I. So, let us trace out the light ray. I will consider that the medium has, the slab has a higher refractive index than the surrounding. For now, I will assume that this is air, right. So, we know that initially it bends towards the normal and it has a lesser angle here. Now, once again if I draw a normal here, and in the next refraction we can say that it comes out from here, and we all know that we have discussed this in the first lecture of refraction, that the final angle at which the light ray comes, what can we say about this angle and this angle? So, even after successive refractions, if the surfaces are parallel, we know that whatever is the initial angle at which it enters, it will come out into the same medium at the same angle, because the refractive index here and the refractive index here are same. So, the angle here and angle here should also be same, which means the final light ray which is coming out into this medium will be parallel to this incident ray. So, this incident ray and this final ray will be parallel to each other, right. But if you observe closely, they are not a single line. If you just extend this further, it will not be this line. So, which means this is the incident ray, this is the final ray which is coming out. If you see, if I just extend the initial ray, you would observe that there is a gap between these two parallel lines, right. So, that gap, that perpendicular shift is what we call as lateral shift in this particular scenario, right. So, I will just extend this so that you will get a better idea. So, if I extend the initial direction of the incident ray, you can see that the final light ray which is coming out is along this direction. Although it is parallel to this particular line, there is this gap. So, that gap is what we call as lateral shift. So, let us calculate that. So, maybe I will just extend this also further. backwards. Now, we need to find the perpendicular distance between these two lines. So, what I will do is I will draw that perpendicular line. So, this line which I have drawn here, so this is what we call as lateral shift. So, this line, this will be 90 degrees. So, let us call this distance as some L. So, that L is what we have to calculate. Now, so in this particular scenario, we can say that, so with the normal, this light ray will be making an angle of R. So, which means even here this angle will also be equal to R. Okay. So, let us see how to calculate this length. So, we know this length as T, we need to find this length. So, how do I use that? So, please observe carefully, I will just extend this normal further in this manner. So, I have just extended the normal. Now, look at this triangle which is formed, I will mark few points here. So, this is A, B and C. So, look at the triangle ABC which is formed, AB, this line and hypotenuse. So, this is a right angle triangle, right. Now, in that small right angle triangle which is formed ABC, so this small right angle triangle, this angle here is R, right. So, in this particular scenario I can say that if I write the value of cos R, so cos R is equal to, this is the adjacent and this is the hypotenuse. So, I can write this as cos R is equal to, this adjacent is nothing but thickness of the glass slab. So, T divided by this hypotenuse which is AC, I will write it as AC itself. So, from this I will get the value of AC as T by cos R. So, that is the expression which we get. Now, we need to find this length. Now, when you look at this triangle which is formed, so this one, so we have AC, let me call this as point D. So, we need to find AD. So, that is what we are looking for. So, we know this length, we know the hypotenuse of this right angle triangle, we have just calculated that. So, if I know this angle, I can easily calculate this length, correct. So, how much would this angle be? So, observe carefully, we know that because this is I, this will also be I, because light enters into the final medium also at same angle, because initial and final medium are same. So, this angle is I and this angle is R. So, if you see here, can I say that if this is I, this complete angle will also be equal to I. So, this and this are the same, because they are just two lines which are crossing each other in this manner, right. So, whatever is this angle, this complete angle should also be same. So, this whole angle is I, this is R, which means this angle will be I minus R. So, I can say that this angle is I minus R, correct. Now, you can easily write the equation for this right angle triangle in triangle ADC. So, in triangle ADC, I can write, we need this length, right. So, I will write sine. So, sine I minus R is equal to opposite, which is the length which we are trying to calculate. So, let me write it as L divided by hypotenuse. The value of hypotenuse is T by cos gamma. So, T by cos R. So, that is the expression which we get, and if I find the value of L, I will be getting L is equal to T into sine I minus R divided by cos R. So, this is the expression for lateral shift. So, that is what we say. So, a glass slab produces a lateral shift in the light rays which are incident onto it. Now, keep in mind, I will just write it down here, a glass slab or any slab, need not be glass, a parallel glass slab, a parallel slab produces a lateral shift but not a deviation for the incident ray. So, deviation basically means changing the direction basically. So, if this is the incident direction, so if this light ray finally by the time it comes out, if it is traveling in this direction or in this direction, then that is what we mean by deviation. Deviation means changing the direction itself. So, here if you see the incident ray and the final ray which is coming out, they are in the same direction. The only thing is that one is along this line and the other one is along this line. So, both are along parallel lines, they are only shifting by some distance. So, we can say that this parallel glass slab is producing a lateral shift, it is producing a lateral shift, but not any deviation, right. So, that is the basic property here. So, students, in each of the earlier concepts which we have discussed in plane mirrors, in spherical mirrors, we talked about velocity of the image formed at the end, right. So, similarly, even now we will be discussing about the image velocity when the object moves. So, the effect that the plane surface refraction creates for the velocity of image. So, I will write it down, velocity of image in plane surface refraction. So, I will explain this with an example. So, the earlier example which we have taken, the fish and bird example, right. So, we will consider the same thing. So, let us consider that there is a fish in this lake and there is a bird. So, this is the bird and there is a fish. So, let us consider a scenario like this. Now, so this bird is let us say this fish is moving and the bird is moving, they can move in different directions. So, let us say bird is moving like this, the fish is moving like this, let us say the velocity of this is some v1, the velocity of this is v2. So, we already know how to find the separation between them as seen by 1, right. We have already discussed the separation at which fish is present as seen by the bird, or at which bird is present as seen by the fish. So, we have already discussed that. So, now we are going to talk about if those are moving, how does one observe the velocity of the other to be, clear. So, if fish is observing the bird, so what will be the velocity of the bird as seen by fish and cases like that, clear. Now, in all these cases wherever we are dealing with velocity related to plane surface refraction, so I want you to follow this. So, the bird is here. So, first mark distances from the interface for the bird and the fish or whichever objects are involved in that scenario. So, first mark some distances. So, here I will be marking them as x and y. I am assuming that bird is at a distance of x from the interface and the fish is at a distance of y from the interface. Okay. Now, once you do this, because we are trying to find the velocity of bird with respect to fish or the other way around, let us choose one of these two cases. Let us solve for one particular case. Which case shall we solve now? Let us solve for velocity of bird as seen by fish. We will do that. Velocity of bird as seen by fish. So, that is what we are trying to understand in this scenario. So, what I will do is to first find this is the method I will be using. I will first find the distance at which bird appears as seen by fish. Clear? First I will calculate that. We already know the method for doing this, we have done this in all the previous class, the distance at which bird appears as seen by the fish, right. We will start with that, and the reason why I am doing is, see, for example, if I know the distance at which something is present from me, and if I now find out at what rate that distance is changing, I can find out the speed with which the other body is moving, correct. So, what I am trying to say is, so if let us say I am standing here and if there is an object, let us say it is moving. Now, how do I find the velocity of that object? One way of understanding it is looking at how much distance the object is present from you and looking at how fast that distance is changing. So, if that distance is changing at a fast rate, then the object is moving faster, or if let us say this distance is decreasing, it means that the object is moving towards you, or if the distance is increasing, the object is moving away from you. So, that is exactly the method which I am going to use. So, I will find out the velocity, sorry, the distance at which the bird is as per the fish, and then I will see how that is changing, at what rate that distance is changing. So, let us do that. So, we are trying to find the distance at which bird appears by the fish, as seen by fish. So, this is the observer in this scenario. Clear? Fish is observing the bird. So, bird is the object here. So, which means the light rays are travelling this way. This is the final medium. This is the initial medium. Now, we already know how to write the expression for plane surface refraction, final medium. Oh, I haven't taken the refractive indices. So, let us call this as mu 1 and this one as mu 2. Okay. So, final medium in this case is this one, which is mu 2, by initial medium is this, which is mu 1, is equal to image distance. I need to find the image distance. So, V divided by object distance. Bird is the object, light is coming from the bird, right. So, what is the distance at which bird is present from the interface? It is x. So, x is the object distance. So, solving this will give me the value of V as mu 2 by mu 1 into x. So, that is the position of the image of bird as seen by the fish from the interface. So, which means what is the distance of bird with respect to fish? So, I will represent it with this expression, distance of bird with respect to fish. So, we can say that from the interface the image of bird appears to be at this distance, which means from the fish the bird appears to be at a distance of. So, let us say the image of bird is formed somewhere over here. So, let us say this is the image of bird. So, we know this distance, right. Now, what is the distance of its image from the fish? That is what I am writing here. So, that would be this length plus this length, and I can write it as mu 2 by mu 1 into x plus y, correct. So, that is the idea. So, this is the distance of bird as seen by fish. Okay. Now, like I told you earlier, if I know the distance at which something is present from me, and if I differentiate it, what am I going to get? I am going to get the rate at which the distance is changing, clear. So, which is what I am going to do exactly now. So, in this particular case I am going to differentiate this. When I differentiate, I will get velocity of bird with respect to fish, velocity of image of bird with respect to fish is equal to, so when I differentiate, I get mu 2 by mu 1 into dx by dt plus dy by dt. Okay, we got an expression. Now, this is where you will have to be very careful while substituting the values. So, let us say in this particular scenario, I have just taken one example to explain this. So, I am considering that the bird is moving downwards and the fish is moving upwards. So, whenever you are substituting the values, remember that these are rate of changes. This is the rate at which the values of x and y are changing. You all know that whenever we have a parameter which is increasing, its rate is positive, right, and if there is a parameter which is decreasing, then its rate is negative. So, that is how you should be substituting the values, not by looking at the directions, not as vectors, but as rates. I will explain you. Let us look at x. So, this distance is x, right. Okay. So, the distance from the interface up to the bird. So, we have taken that length as x. Now, think about what happens to this x as the bird moves down. As the bird moves down, what happens to x? It decreases, right, because bird is moving in this direction. See, this is an assumption. I have just taken it to be downwards. You can take any direction. I am taking one direction and showing you how to substitute the values, clear. So, we have assumed this as x and we got the final expression for velocity, but While substituting, look at the direction of bird's velocity, and because of that velocity, what is happening to x? X is decreasing. If x is decreasing, then rate of change of x is negative. So, what I am trying to say here is this expression should be taken as mu 2 by mu 1 into dx by dt should be substituted as minus v1, because x is decreasing at a rate of v1. So, because of the motion of bird downwards, this length is decreasing at a rate of v1. So, that is what we will have to substitute there, and because it is decreasing, I will substitute minus v1 plus dy by dt. So, dy by dt, let us see if y is changing or not. I have taken that even the fish is moving. So, if the fish was at rest, right, if the fish was at rest, then dy by dt is 0, because the level of water is not moving, the fish is not moving, then I can substitute dy by dt is 0, right. But here I have considered that the fish is also moving. If the fish is moving, then y changes. Now, by looking at the direction of velocity of the fish, think about whether dy by dt is positive or negative. You can say that easily now. Because of the motion of fish, y decreases. So, which means the value I should substitute there should be minus v2, right. So, this is minus v2. So, once again I am reminding you, so that do not think that this is going in the upward direction, this is positive direction, I should substitute positive value. I am not substituting vectors there, I am just substituting the rate of change of x and y. So, in this case, because of the motion which I have considered, both x and y are decreasing. So, both the values should be taken as negative, right. Now, it is not over. I finally got the velocity of bird as seen by fish, clear. Now, let me rearrange the terms and write it over here. Velocity of the image of bird as seen by fish is equal to, you can see that there is a negative sign which is common, right. If I take that negative sign out, I can write it as mu 2 by mu 1 into v1 plus v2. So, which means I definitely know that this term here is a negative term. I am getting a negative value for velocity, you can see that, right. Now, what does that negative sign here imply? What does this negative sign imply? Does it mean that the bird is moving downwards, or how do we understand that, right. So, I have told you earlier, throughout this analysis, the signs, whatever signs we are getting, whatever signs we are substituting, all those will represent rate of change, whether the parameter is increasing or decreasing. So, here I have got a negative value, it means that the bird, or for the fish, the bird appears to be at some distance, and the distance at which the bird appears as per the fish, that distance is decreasing. So, this negative sign implies that the separation between the bird and fish as seen by fish is decreasing. Clear? So, which means now from here the bird is, the fish is looking at the bird. So, it appears to be at some distance. Now, if that separation between them is decreasing, what will the bird think? Bird will automatically think that the fish will automatically think that the bird is moving towards it. Clear? So, whenever we get a negative value, separation decreases. Decreasing separation means that the other body is moving towards you. Clear? So, that is how we can understand. So, that is the scenario. So, just like I have done for case 1, I would like you to try for case 2. You know the case 2. What is case 2? Velocity of fish as seen by bird. So, write down a similar expression for that, and I would want to see that in your notes. I want this expression finally, or that expression, whichever. So, just like we have found velocity of bird with respect to fish, find velocity of fish with respect to bird. Clear? So, you can just write it in terms of variables, the same variables which I have used for the same case. Bird is going down, fish is going up. And once again, please understand properly what negative signs and positive signs mean here. So, negatives and positive does not mean direction of positive direction and negative direction. Positive means increasing distance, negative means decreasing distance. So, based on that you should understand the direction. Clear? Students, now we will solve a question to understand the concept which we discussed earlier, right. So, the question is like this. So, same case where we have the fish and the bird. So, let us consider that the fish is at rest this time, it is not moving, it is at rest, and the bird is moving vertically upwards, and let us consider that the speed of bird is some 6 kilometer per hour. So, that is the velocity of bird. This is water, you know the refractive index of water 4/3. Okay. So, the bird is at rest. So, this time let us solve for the velocity of fish as seen by bird. Clear? So, I need to find velocity of fish as seen by bird. Okay. So, we know that to find the velocity, first I will have to find the separation between them as per the bird, clear, in the point of view of bird. So, let us write it first. So, because bird is the observer here, so this is the observer. So, the light travels from the fish to the bird. So, this is the final medium and this is the initial medium. So, if I substitute the values, final medium, okay, we need to first assume the distances. So, let us call this as x and this distance as y. Okay. So, the final medium has a refractive index of 1, air, right. So, 1 divided by the initial medium has a refractive index of 4/3. So, 4/3 is equal to, so this is the object, right. So, let me consider that the image distance is some v and the object distance is y. So, simplifying this will give me the value of v as y by 4/3, which is 3y/4. Okay. So, that is the idea, which means the bird sees that the fish is at a distance of 3y/4 from the interface. Now, what is the distance at which it is present from the bird? So, the separation between the fish and the bird as seen by bird, or the distance at which fish appears as seen by bird. This is equal to, so this is already x and this y now appears to be 3y/4. So, x plus 3y/4. Now, we need to find the velocity of fish as seen by the bird. So, I will just differentiate this expression. So, differentiating it will give me velocity of fish with respect to bird. So, yeah, when I differentiate, I get dx/dt plus 3/4 times dy/dt, correct. So, dx/dt. So, dx/dt, we know that this level is anyways fixed, the level is not changing, right. So, x is only increasing from this side. So, from here the x value is increasing, and the reason why it is increasing is because of velocity of bird, right. So, can I directly write dx/dt as velocity of the bird itself, and because x is increasing, bird is moving up, x is increasing. So, the value of dx/dt will be positive. So, this will be plus 6 plus 3/4 into dy/dt. So, this y, neither the fish nor the level of water, none of them are changing. So, this is not moving, this is also not moving. So, which means y is fixed, y is not changing. So, dy/dt will be 0. So, this is 0. So, simplifying this will give me 6 km/h. as the final answer, and you are getting a positive value here. Now, what does positive value mean? Once again, it means that the bird thinks that the separation between the fish and the bird is increasing. So, that is what it means. So, the bird which is going up, if it watches the fish, let us say somehow it watches the fish. So, it thinks that the separation between those two is increasing, clear. So, that is how it perceives. So, that is what this positive sign here indicates, clear. So, students, we have completed almost all the concepts from plane surface refraction. So, we will solve some questions now based on the whole topic starting from Snell's law, right. Okay. So, here in this question it is given, if the incident ray is retracing its path, they are asking us to find the angle of incidence. So, a light ray is incident onto a triangular prism. So, this is called a prism. So, it is incident at some angle I. So, it enters into that prism. So, the angle here is given as 30 degrees and this angle here is 90. So, this surface here is a silvered surface. So, which basically means that it is a reflecting surface. So, as the light ray goes here, it gets reflected. Okay. So, they are asking us to find out the condition for retracing. So, you all know what is the condition for retracing. So, if I just extend this normal further, so we know that this light ray will retrace if it strikes that mirrored surface perpendicularly, right, normally. So, it means that because this is vertical, this refracted ray should strike this way. So, it should travel horizontally and then strike the surface normally. So, when this occurs, it just turns back everywhere and just retraces its path. So, that is the idea. So, we need to find this angle. So, based on the information, I guess we can calculate this angle, right. So, how much would that angle be? This is 30, this is 90 once again, which means this will be 60, right. So, if this angle is 60, we can say that this angle will once again be 30 degrees. So, we can easily say that this angle which I have drawn there is also the angle of refraction at that surface. So, I can apply Snell's law there. So, for this surface, if I write Snell's law, so I can write outside medium which is air. So, 1 will be the refractive index into sine of angle with normal is sin I is equal to here the medium has a refractive index of root 2 into the sine of angle with the normal is sin 30. So, sin 30. So, simplifying this, I will be getting sin I is equal to root 2 into sin 30 is 1 by 2. So, which means sin I is 1 by root 2 implies I is 45 degrees. So, that is the angle of incidence in this case, clear. So, now we will see next question. So, here it is given that a ray of light travelling in a medium of refractive index mu is incident at an angle theta on a composite plate containing 50 plates of refractive index 1.01 mu, 1.02 mu, 1.03 mu, so on till 1.50 mu, 50 plates, right. So, the ray emerges into a medium of refractive index 1.6 at an angle x then. So, they have given us some options. So, let us first draw the diagram regarding this scenario. So, they are saying that there is a composite plate. So, let us represent that composite plate in this manner, and it has multiple thin plates in it. There are 50 such plates according to what is given in the question, so on till the last plate. So, there are 50 plates in this composite slab, and the final medium is given to have a refractive index of 1.6, and the initial medium has a refractive index. The ray of light travelling in a medium of refractive index mu is incident. Okay. The initial medium has mu and the final medium has a refractive index of 1.6 mu. So, this should be 1.6 mu, right. Okay. So, this is what we have, and the light ray is travelling through all these media. They have given the refractive index of each of these thin slabs. So, this is 1.01 mu, this is 1.02 mu, 1.03 mu, so on till this is 1.50 mu. Okay. So, they are saying that the light ray, let us represent that light ray like this. So, this light ray is incident at an angle theta. So, it undergoes refraction at each and every surface, it enters, strikes this surface, undergoes refraction, again undergoes refraction. So, it undergoes multiple refractions, and let us say it finally reaches here and it comes out of this surface at an angle of x, and it enters into this 1.6 mu medium. Clear? Now, we already know that because these are all parallel glass slabs, we do not have to worry about what is happening or how many refractions are happening in between, how much is the refractive indices of those media. So, I can directly write Snell's law, I can directly equate the product of mu and sin theta for the first medium with the last medium also, without even worrying about what is happening in between. So, you all remember this, right? So, I can directly write that, I do not have to worry about the multiple refractions happening in between. So, I can directly say mu into sin theta. So, mu into sin theta is equal to, here it is coming out at an angle of x and the refractive index of this medium is 1.6 mu. So, 1.6 mu into sin x. So, that is it. So, mu and mu gets cancelled, and we will be getting the value of, they are asking sin x in the question. So, I can get sin x is equal to 10 by 16 into sin theta. So, which is nothing but 5 by 8 sin theta. So, that should be the answer, right. So, we will see a few more. So, students, let us solve some more questions. So, the first one here, it is given the xz plane separates two media A and B of refractive index mu 1, which is 1.5, and mu 2, which is 2. A ray travels from medium A into medium B. Its directions are given by unit vectors ai cap plus bj cap, and this is the incident rays unit vector, and this is the refracted rays unit vector. And they are basically asking us to find out the relation between their coefficients, the coefficients of I cap and j cap in the respective unit vectors. So, let me first draw the diagram which represents this. So, I will take this as the interface. So, as you can see, xz plane is the interface, right. So, if I consider this as x, this as y, and outward direction as z. So, xz plane will be like this. So, this plane is the interface. So, xz plane is the interface which will make this y axis the normal. So, this is y and that is also the normal. Okay. Now, let us represent the incident ray and the refracted ray. So, you can see ai cap plus bj cap. So, let me represent that something like this. So, I will call this as medium A and this as medium B, which means according to what they have given, the refractive index of medium 1 is 1.5. So, this medium has a refractive index of 1.5 and medium 2 has a refractive index of 2. So, 1.5, 2, and incident ray is travelling from A to B. So, it is travelling from A to B. So, if I represent the incident ray like this, so it is incident in this way. So, after entering into this medium, because it has a higher refractive index when compared to this, it moves slightly towards normal. So, let us say this is the refracted ray unit vector. So, this is a unit vector and this is also a unit vector, which means both have a magnitude of 1 each. Okay. So, they have given us the unit vector in component form, right. Okay. Now, we know that obviously to find out the values of A, C, B, D or the relation between them, I will have to apply Snell's law here, and when I have to apply Snell's law, I need to know the angle that each of these unit vectors make with the normal. So, I need to find this angle and this angle, correct. So, what I will do is, I will just use this vector in its component form. They have given that it is ai cap plus bj cap, which means this unit vector can be understood as ai cap, right, which means a vector in this direction with a magnitude of a, and bj cap. So, this length would be b, correct. ai cap plus bj cap will be the unit vector. Now similarly, if you look at the refracted ray is Ci cap plus Dj cap. So this length will be D and this length will be C. So this is C, this is D, correct? Or maybe I will represent them in different color. The incident ray is this and the refracted ray is this. So these are their components, Ai cap plus Bj cap, Ci cap plus Dj cap. Okay. Now by looking at these magnitudes I can easily find out the angles also, correct? Okay. So now let us write Snell's law. So Snell's law, the normal is the y axis. So we can write Snell's law as product of refractive index and sine of angle with normal. So for the first medium it is 1.5 into what is sine of this angle? This is I, let us say this is R. So what is sine I? You can look at the triangle. What is the value of sine I? Remember that this is A, this is B and this is 1 because we have considered a unit vector. Similarly, this is D, this is C and this is 1, correct? So what is sine of I? So sine I is opposite by hypotenuse, which is A by 1 or is equal to, for the second medium has a refractive index of 2, right? And sine R, what is sine R from that triangle? Opposite is C, hypotenuse is 1, so C by 1. So that is what we get. So simplifying this, you will be getting, they are asking us A by C value. So A by C is equal to 2 by 1.5, 2 by 1.5, which is equal to 4 by 3. So that should be the answer. So in this particular case, we cannot comment on the values of B and D or the ratio of B and D. So we just have to leave it that way, clear? So that is the basic idea. So we got the value of A by C. Okay, now let us move on to the next question. So here they are saying that the observer can see the topmost point of a thin rod as shown. When liquid is filled up to a height of 2h, he can see the lower end of the rod. Find the refractive index of the liquid. Okay, let me first explain this scenario. So this is basically a container. It has a height of 3h, a width of 2h, and at one edge there is a object of height h which is placed. Now this person, he is seeing it, he is seeing the topmost point of this object using this particular line of sight. You can see that in the diagram, right? So he is only viewing through a small narrow tube. Let us consider that this is a narrow tube. So he is looking through that tube. So which means he will be able to receive light rays which are only coming in this direction, clear? So he can only receive light rays which are coming in this direction. Okay, so now what they are saying is, earlier as you can see from the diagram, he is looking at the topmost point of the object. So that is what he is looking at, which means the light rays which are coming from here will be able to directly enter into his eye. So no other point he can see, because a light ray, the point which, let us say if I consider a point here, the light rays which are coming from here cannot enter into this tube in a straight line, clear? So let us say they get reflected and they get absorbed. So he can't see this point. So you can easily understand this, even if you make a narrow tube and look through it, you can only see at one point, right? So this is a scenario like this. Okay, so initially he is seeing the topmost point, right? Now look at the question that they have given here. When liquid is filled up to a height of 2h, he can see the lower end of the rod. So which means if I fill liquid in this up to a height of 2h, this whole height is 3h. So if I fill liquid up to a height of 2h, then somehow this person is able to see the bottommost point. So that is what is given. So we will have to find out the refractive index of the liquid. So this is a previous JEE question. So let us see how to analyze this. So let us first draw the liquid level. So they have given that it is filled up to a height of 2h. So up to 2h, let us say this is 2h. So let us say liquid is filled up to here. Now think of it like this. What happens when I fill it with liquid, when there is liquid filled over here throughout this region? What is going to happen? Look at what happens to this ray. So look at this ray. So earlier this ray was traveling like this, and moving in a straight line and entering into that tube. So, there was no problem. But now, when this light ray, let us say if it is starting from here and traveling like this, by the time it reaches here, it can't go in a straight line because of the interface between air and water. So, what happens to this light ray here is that it bends away from the normal, because if I draw a normal, so this is denser medium, this is rarer medium. So, this light ray, by the time it reaches there, it refracts and bends away from the normal. So, this light ray which is starting from here, it goes still here, bends and then goes like this. So, it can't enter into that tube. So, that is why he can't see the topmost point now, right. But they have told that now he can see the lower end. So, which means after filling the liquid, if I consider a light ray which is coming from the lower end, then that light ray will enter into that tube. Do you understand that? So, earlier the light ray coming from here was straightly going through the tube when there was no water or liquid, clear. Now, after filling it up with liquid, they are saying that a light ray which is starting from here is entering into that tube, clear. So, that is the idea. So, which means if I take a light ray from here up to here, so if I consider one incident ray from the bottommost point like this. So, this light ray is the one which undergoes refraction at this surface and then it travels in this direction and enters into the tube. I hope you understand this. Earlier when there was no water, light ray started from here and it went through in a straight line. But now that water is filled, this light ray won't be able to travel in a straight line, correct. Another light ray which is starting from somewhere over here at the bottommost point will strike the surface, undergo refraction and then enter into the tube. So, that is the reason why he is able to see this point even though he is pointing towards this position, because bending is happening in between. I hope you are getting this. So, he is trying to look at this position, but the light ray which is starting from here is the one which is traveling towards him. So, he is able to see this position. Is that clear? So, that is what we will have to solve for, right. So, they are asking us to find the refractive index of liquid. So, now that we have established what is happening in this particular scenario, let us write the equations. So, we can say that light ray starting from here is traveling like this, undergoing refraction at this surface and entering into that tube for that person to see. So, which means if this is the angle of incidence, this is the angle of refraction, clear. So, let us write Snell's law and find out the value of mu. So, let us write that. So, before that I need to find some angles here. So, let us see some distances also. I will drop one line. So, we know that because this is 2h, this length will be h. Why is it h? You can easily say, if you look at this straight line, the original light ray and this horizontal line, I can easily say that this angle and this angle are same, clear. And similarly, you can see here that this length is h, right, and this length is also h, because liquid is filled up to 2h, which means this triangle which is formed over here, please look carefully, this triangle which is formed and this triangle are congruent triangles. Is that clear? H, H, angle, angle, 90 degrees, 90 degrees. So, they are congruent triangles, which means that this horizontal length and this horizontal length should also be same. So, we can say that this length is h, this length is h, which will automatically make this angle 45 degrees. If this is 45, because this is h, this is h, this is 45. This is 45, angle of refraction is also 45. So, now we know angle of refraction as 45 degrees. Okay. Now, let us find angle of incidence. Now, you know that once again this length is h, we have just understood that. So, this length is h, correct, and this vertical length is 2h, correct. So, let us find I value. I mean, we need sin I value to write the equation. So, let us directly write sin I. So, sin I is equal to opposite h by hypotenuse. Hypotenuse is this. Because this is h and this is 2h, I can say that the hypotenuse will be root over h square plus 2h square, right. So, you can cancel out h in the numerator and denominator and you will get 1 by root 5. Okay, I have all the values which I need to write the Snell's law. So, let us write it. So, this is the normal, this is the angle of incidence. So, Snell's law. So, this medium has refractive index mu. So, let us write mu times sine of angle with the normal, which is sin I, which is 1 by root 5, is equal to outside. Outside we have air and the final direction of refracted ray is making an angle of 45 degrees with the normal. So, we can say 1 into sin 45. Sin 45 will be 1 by root 2. So, simplifying this will give me the value of mu as root over 5 by 2. So, that should be the answer. So, this is a very good question. So, please understand carefully what is the process that is happening there. So, I'll quickly give you a summary once again. The light ray, when there was no water, the light ray was starting from here and directly going in a straight line to enter the eye of that person. But now that the water is filled, we know that as light rays travel from here outside, they bend. So, because of that bending nature, the light ray which is starting from here is the one which is striking the interface and then entering along the same line. Clear? Because he can receive light rays only along this line. I hope that is clear. So, the light ray which is finally coming along this line is the one which is starting from here. So, incident ray after bending it is going along that 45 degree line so that the person can see. So, that is why eventually he will be able to see this position, right, even though he is not pointing towards it. So, that is the idea. Okay, so, that is about refraction at plane surfaces. So, in the next lecture we will be discussing about total internal reflection, which is a very interesting topic and which has a lot many applications in our daily life scenario. So, we will see that.